electric charge. So what are the common features or differences? Well, there are lots of differences between mass and charge, electric charge. Mass is always positive. Or if you have no mass, of course, mass is equal to zero. I mean, it's believed, it's assumed, especially in Newtonian, in classical context, to be a positive property. Mass is expressed positively, with positive numbers, real numbers. 1 positive. Why is that? Is that useful to assume in Newtonian mechanics that mass is positive? I think it is rather useful because, if you think about Isaac Newton's fundamental equation of dynamics, it's saying essentially that, the force is equal to the mass times acceleration, which actually means that the acceleration which a body acquires when it undergoes the action of an external force is directly proportional to the intensity of that force, and so forth, and inversely proportional to the mass, the thing we call mass. It's inertial mass, it's all about inertia. But hang on. I just want to say that if mass would be negative, what would happen if this table would undergo a force of mine, okay? You see that if I exert a force, I act with a force towards, in this direction, in that direction, the table acquires some kind of acceleration in the same direction. If the mass of that table would be a negative number, when I push in that direction, the table would hit me. It would move, of course, in the opposite direction. This doesn't happen. Thanks God. It would be a difficult world to live in. But that's essentially all. Mass quantifies inertia, what I have been speaking about. This Newtonian law which combines acceleration, which acquires a body when it undergoes a force, doesn't depend only on force, it also depends on something else, another property of that body. And that's inertia. And a quantization, if you want, quantification of inertia is inertial mass. The M in Isaac Newton's law is called inertial mass. The bigger the mass, the greater the intensity of the force should be if you want to cause acceleration on or with that body and so forth. So this all reflects the fact that all bodies have a property according to which it tends to maintain its state of rest or uniform rectilinear motion, inertia. Quantization of that in terms of forces and acceleration to other concepts is called inertial mass. That's how a physicist, Newtonian physicist, defines, if you want, mass. And remember that in physics, when you want to define something, define means, for a physicist, how do I measure it? That's the definition of physics. It's not, when you know how to measure something, you can think philosophically about it and try to see what it is and how you understand it and how you can picture it and so forth and so forth. That's of course important. Very important. But first, if you want to do physics and you speak about mass, charge, magnetic field, electric field, vector bundles and whatever you invent, you have to tell people, how do I measure the charge? In a very simple, concrete experiment. The charge, the mass, the force, electric field, magnetic field, that's physics. You understand a physical quantity if you know how to measure it. Not just measure it, you have to tell people how. You must put the emphasis on the procedure. When you define a physical quantity, its definition is really the procedure with which you measure it. the unit, the measurement unit which you use is conventional, it's not important. Well, sorry about this digression, but it's important to stress because, you know, electromagnetism has introduced new concepts, new quantities, and you have to be able to tell people how you measure them. Mass has another property. It has an active property which is called gravity. Any mass causes around it gravitation. It's interesting that you should feel gravity towards this table, towards this object, towards everything. And mass passively responds to gravity. This table will equally respond to the gravitational attraction or pull generated, for instance, by the Earth we are standing on. Okay? And then an important thing, you probably have heard that about the fact that in classical physics, mass is conserved. The total initial mass and the total final mass, if you add up correctly and carefully all the pieces of your processes, mass seems to be conserved. Well, that's more or less the only totally, if you want, common property with electric charge. Electric charge is another property that these objects in nature can have. And charge is conserved. Total charge must be a conserved quantity. If you look at particle physics by interactions, electric charge on the right-hand side and on the left-hand side must be equal, and in chemistry as well, I suppose, and so forth. The difference is that electric charge does not respond, at least it seems, in classical physics, does not respond to gravity. Charge does not generate gravity. It's the mass, which is actually the gravitational mass. It's another problem, but I will speak about this later. Charge is unrelated to inertia. If you have this table with zero electric charge, neutral, as it is now, globally looking at it, or if this table would, or if you consider the situation where this table would have an enormous, for instance, positive electric charge, the effect of forces doesn't change the value of acquired acceleration if you neglect the electric interactions. I mean, conceptually speaking, so that means that charge is something, is a quantity, which we can introduce in our models, but it's unrelated to inertia. And charge can be positive or negative, and that's a big difference between mass. We have said that mass is usually considered to be always positive. Okay? So here we have an electric charge. And you also know about the similarities and differences between electricity and magnetism. They seem to be very different things, right? There are two types of charge and there are two types of magnetic poles. Seems to be rather similar. The electric charge that an object has is non-permanent. It's not a permanent thing, right? If this table would be isolated from the rest of this lecture theatre, and if it would possess an electric charge, well, if you touch it, if you realize a contact, there would be loss of electric charge, there would be a charge flow from the table to the rest of the world, right, eventually. And so charge can be lost or acquired through contact, right? And, of course, you can have in space isolated electric charges, right? For instance, point-like small particles, well localized in space, and which have an electric charge. That is not possible for magnetism. You cannot have an isolated magnetic pole alone, you see what I mean, in space. You can't have a north pole alone in space without somewhere attached to it a south pole. There are no magnetic monopoles in classical physics again. You know all these experiments which suggest to us to break a magnetic bar with a north and a south pole in two species. You might think, well then, if I'm quick enough, I'm going to separate the north pole from the south pole, but that sort of thing doesn't happen. Immediately you generate two small dipoles, not monopoles, dipoles, both having a north and a south pole, north and south pole. That is what happens. So magnetism is different than from electricity, you see. And magnetism, once you become magnetic, unfortunately, it's permanent, or fortunately, it depends. If I have a magnetic bar, if I touch other metals or other magnets, it doesn't lose its magnetic property. If you hit on it with a thing, it doesn't lose its properties, right, of magnetism. The only thing you have to be careful about is the temperature, the famous Curie temperature, above which a magnetic material should lose its magnetic property. But that's the thing which I'll mention later. And of course, yes, these are a few similarities which you might have known about. And here we are then. If two electric charges can repel each other or attract each other, what can we say about the intensity of the force which acts between these charges? Well, that has been achieved by the French physicist Coulomb. And the law is the Coulomb law. And when a force has this type of dependence, physicists usually say, well, it's a Coulomb type interaction. It's a Coulomb type interaction. Look at the structure of this law, okay? The intensity F of the force between two electric charges, which are represented by Q1 and Q2, right? Q index 1 and Q index 2 just represent the values of the two electric charges. So the product of the two charges, and then you have a 1 over r squared. 1 over r squared. That's like Newtonian universal gravitation. You remember the inverse square law, so it's very similar. And then you have a proportionality constant, which is represented by k. In reality, it is, as you know, something like 1, the bottom line, the bottom equation, 1 over 4 pi epsilon naught, index 0, or naught, as we say in England. Epsilon naught is something which is called the dielectric or dielectric constant of vacuum. The value of 1 over 4 pi epsilon naught is high in standard international units, the standard international unit system, kilograms, meters, and newton for force. So it's roughly 9 times 10 to the plus 9 billion if you want, newton times meter squared over kilogram squared. It's quite important. And the force can be attractive or repulsive according to the sign of the product between the two charges, and so forth, and so forth. And you see the title there, Another Triumph for Isaac Newton? Well, yes, it seems at first sight, because the model for the electric force is similar to the model for gravity, right? Gravitation is an action at a distance. It has similar mathematical properties. It is an inverse square law, and so forth. And there are, of course, fundamental differences as well, as we will see, as you know. You can compare gravitation with the electric force. Well, you see, the common points in red, the differences in blue, or that is really good. Yes. The common point is that gravitation is an action at a distance. Okay. instantaneous action, that means, okay? Like the electric force on an electric charge, or between electric charges, simply. Both are inverse square law. Inverse square laws. They have the same mathematical structures if you compare masses with charge as well. Now the differences begin with the proportionality constant. The proportionality constant in Newton's law for gravitation, right, is called big G, capital letter G, and that's Newton's universal constant of gravitation. Its value, I haven't written it there, but you probably know it. It's 6.67 10 to the minus 11 Newton times meter squared over kilogram squared. So in the same units, it's comparatively